Let's look at another example of a differential equation which will show us how to use Euler's method is how we're going to solve it. That's based on the tangent line approximation and on implicit derivatives. And so this will be a little bit of a review of that, and then also a lead-in into integration. So the differential equation I want to look at is y prime equals 2x minus y. Pretty simple equation. It's a differential equation. It's an equation. It's got an equal sign. That's what equation means. And it's got the derivative and the function. Y is a function. If you see the derivative, then y has to be a function. We only take derivatives of functions. Okay. So this tells us already where y is increasing or decreasing. So y is increasing if 2x minus y is positive. So that means y has to be less than 2x. So that's just a little tiny bit of algebra. And what I'm going to do is draw the line y equals 2x. And we'll know on one side y is increasing, the other side y is decreasing. And so, so there's our situation. I better look at my notes. Yeah, so on this side y prime is negative. On this side y prime is positive. I'm going to color code these. Okay, so the second derivative is, that's where we have to use implicit differentiation because y is a function. So let me just start taking the derivative. I have y prime is 2x minus y. So if I take the derivative of each side, the derivative of y prime is y double prime. That's what we're looking for. Derivative of 2x is 2, and the derivative of minus y is minus y prime. The thing is, we've already gotten a formula for y prime, so I've done this implicit differentiation step right here, down here, and it says, oh, y prime, but I know what y prime is, so I'm going to do the substitution. This is 2 minus 2x plus y. So y double prime is positive if 2 minus 2x plus y is positive, so that means that y is greater than 2x minus 2. So this is the amount of algebra that we've got to do here, and so I took the derivative of y prime. I said, oh, I already have a formula for that, so I plugged in that formula, and now I know where y double prime is positive and negative, and so that tells me the concavity. This is going to divide the plane into 3 regions. So the thing happens where y is greater than 2x minus 2. So I'm going to draw that. And to one side of that, the second derivative is negative. That's on the right. And on the left, the second derivative is positive. So now we have complete look at the concavity of y, and we're just going to fill this in these 3 strips that go through the plane. So first we have on the leftmost one, y is decreasing and concave up. That's pretty easy to take care of. And then in the middle strip, y is increasing and concave up. I'm just doing this by the signs, S-I-G-N-S, of the derivatives. And in the rightmost region, y is decreasing and, y is increasing and concave down. So there is the 3 regions, and you can see what's supposed to happen in each of these regions. And so what that tells us is that we can get the solution curves pretty accurately, actually. And so here's what's going on. I've just drawn a little cartoon with the strips. And in the leftmost part, we have decreasing concave up, then increasing concave up. So that takes care of these 2 pieces, decreasing concave up, increasing concave up. And then we're going to have increasing concave down. And those are the solutions. The black ones are the solutions. So I've done this using the implicit derivative and what we know about concavity and the mean value theorem. The mean value theorem. I forgot to say mean value theorem. That's the thing that tells us it's the signs that determine the behavior of the function. The sign of the derivative determines the behavior of the function. Okay. So let's go on a little bit and talk about another way that we can get this. This is going to kill two birds with one stone. I hope you're not a vegan. If you are, I apologize. We'll kill two tofu turkeys with one stone. And what this is, we're going to talk about the direction fields and also numerical solutions. And these are all based on the tangent line approximation. So let's make a little box where we can put this. This is the Euler method. And the Euler method says you take the tangent line approximation. The tangent line approximation is, in this situation, it looks like this. I'm going to, let me write it out and then say what I've done. So the tangent line approximation, this is just the equation of the tangent line. And so what I have is y minus f of a is the value of the function, is equal to, well, this is in point slope form, by the way, which is why I'm so insistent on point slope form, because that's the right form for calculus. We've got the slope of the tangent, that's f prime of a, times the change in x is x minus a. And if we do a little manipulation here, if we go to a point a plus h, what we have is that y minus f of a is f prime of a times h. This is saying x is a plus h. This is the same kind of h we had when we were looking at the derivatives. So h is a little horizontal change. And so the Euler method says what we're going to do is pick a small h. That's a tricky thing in practice, so you might have to give it some give and take. And then we're going to start at a known point, and we're going to follow the tangent line approximation to a new point. And then from there, we're going to follow the tangent line approximation to another new point, and another new point, another new point, another new point, and come up with some kind of a solution. So what we have here are, let's suppose that we're still using the same differential equation, by the way. Let's suppose we start at the point 0, minus 1. So I have y of 0 is minus 1. That's the point that we have. Y prime of 0 is 2 times 0 minus 1. That's what the differential equation tells us. It tells us what y prime is, and so we just have the differential equation was y prime is 2x minus y. So I've got y prime equals 2x minus y. And so that gives us the slope there is 1. And so what we're going to say here is that y of 0.1 using the tangent line approximation is approximately y of 0, which is minus 1, plus the slope, which is 1, times h. H was 0.1. I've moved over by 0.1. And so this is minus 0.9. Just a little bit of arithmetic there. It's really actually quite simple. And so so that gives us the point 0.1 minus 0.9. And then we do that again, and we'll do it at 0.2, and then we'll get a new slope, and then we'll do it again, and do it at 0.3, and so forth and so on. So that's Euler's method. That's almost the same thing as doing streamlines, and let me run that by you kind of lickety-split, which is, I've put in this grid here. So what the streamlines do is say, well, the tangent line is close to the actual solution when h is small. So this takes, instead of the curve, it says, well, I'm going to just take a little segment of the tangent line and draw that. And that's going to give me some idea of how the solutions will come together. And if you piece those together, you can get those nice streamlines that you've seen pictures of. So I've got a bunch of points on this grid here, and I'm going to say, well, let's see. Remember, y prime is 2x minus y. And so at the point 1, 2, we have that y prime is 2 times 1 minus 2. Wow, that's 0. I'm sorry, I wasn't expecting that. That's okay. It is what we get. So I draw a little segment with slope 0. And then let's look at 2, 1. Y prime at 2, 1 is 2 times 2 minus 1, which is 3. So I draw a little segment of slope 3. And at 1, 0, y prime is 2 times 1 minus 0. So I draw a little segment of slope 2. At 0 minus 1, y prime is 2 times 0 minus 1. Well, that's slope 1. And so what we've done here in pink is started to do some of the direction field. So you've seen lots of pictures of that. These methods both really depend on having some kind of computational device, because no one step is hard, but man, there are a lot of steps. And so here's the deal. We've used implicit differentiation. We've used the mean value theorem. We've used the tangent line approximation. That's it. That's what we do in calculus. And so that is how we analyze these models. Now, in order to do this exactly, we're going to have to learn how to integrate. So that's going to be our next thing, but one thing at a time. So I'll take a scan of this, put this up on Moodle, and we'll just all make models and just don't sniff any glue.